Okay, Marisa, we're recording for day 2.
Okay. I have the privilege and the honor to introduce here Chandralekha Singh. She is one of the pioneers in the most qualified colleague in research in teaching learning quantum mechanics. I don't remember if I met her in 2019 in Chicago APT, but I remember that I invite her in, and I asked her cooperation, inviting her in GIREP in 2014 in Minneapolis AAPT meeting. Thanks a lot for accepting to give a keynote here in Malta webinar. I hope you will cooperate in teaching learning quantum mechanics GIREP community, which is born in 2019 and is still active with 15 people. Now, Chandralekha Singh is a professor in the Department of Physics and Astronomy and the founding director of the discipline-based Science Education Research Center in the University of Pittsburgh. She is the president of the American Association of Physics Teachers, and she is, congratulations a lot. And I am so happy because we cooperate with the AAPT since a long time. We have an agreement, an official agreement, and we are really happy that we respect so much, become president. Chandralekha Singh obtained her bachelor and master degrees from the Indian Institute of Technology, Kuala Lumpur, and her PhD in theoretical condensed matter physics from University of California, Santa Barbara. She was a postdoc fellow at the University of Illinois, Urbana-Champaign, before joining the University of Pittsburgh. She has been conducting research in physics education for more than 2 decades. She co-led the US team of the International Conference on Women in Physics in Birmingham, UK in 2017. And I thank her for that, because for me it's a very important aspect in our professional work. She is a fellow of the American Physical Society, of the American Association for the Advancement of Science, and American Association of Physics Teaching. And she is a member of the working group developing key concepts for quantum information science learners. I read just recently a paper in which National Science Foundation and White House Office of Science and Technology Policy initiate collaborative effort to develop critical resources for quantum education. This is very, very important. I want to mention that Chandralekha Singh published more than 1,000, I believe, papers related to physics education research of learning quantum mechanics, quantum interactive learning tutorials, research on validated, standardized assessment instruments and longitudinal assessments, technological enhancing learning, intuition and expertise in physics, metacognition, not less in problem solving and scaffolding and transfer. Analogical reasoning is isomorphic problems, role of representation in problem solving, and research on professional development of teacher, learning introductory and advanced physics, equity and inclusion in physics learning. My opening talk was on the perspective which we have to consider COVID for the future and for the inclusion for science learning for everybody. So thank you so much, Chandralekha, to give us the honor of your contribution. I'll leave you. You have 30 minutes starting from now. Thank you so much.
Well, thank you so much, Marisa. I really appreciate, being here. And I'm really delighted to see you and everybody else whom I'm seeing here, and everybody else, hello, even though I don't see you. So since quantum mechanics is not intuitive, I wanted to first start out by talking about a research study that I did that focused on the role of intuition and in physics problem solving. So, we always say that physicists think like, there is something to be said about thinking like a physicist. But the question is, what does that mean? As a researcher, can I actually distill those qualities and then try to help our students learn those things? So in order to do this research, you have to actually give to physics instructors the same kind of problems that you would give to students. Because when we are asking students to solve physics problems, we are actually asking them to think on their feet and solve those problems, because we don't give them exactly the same problems that we have actually, done in the class. What we give them is a transfer problem where they have to use the same principles of physics and then apply it in another situation. So we wanted to see if we could actually do that with a professor, and we give them a problem in which they do not have any intuition about how to solve it. Will they solve it differently from the students? Because that would tell us something about what it means to think like a physicist and what happens when professors' intuition fails. And this can also help us in thinking about how to help students learn quantum mechanics for which they do not have intuition. So let me start out by this research study in which we gave to 20 physics professors and more than 2,000 students a physics problem about which even professors don't have intuition about how to solve them. And they were asked to solve it in an interview situation. So we give them the problem. We went to each of them separately in their office, and we asked them to think aloud about how they would solve this problem. And here is the problem. So you have a spinning wheel that spins for some time, and then it falls on the ground. It slips for some time, and then finally it starts to roll without slipping. And so V final becomes equal to R times omega final. And the question is, how will this final speed, V final, depend upon the coefficient of kinetic friction on the surface? So in other words, if the kinetic friction was higher, would that mean that the wheel will start to roll at a smaller speed, the same speed, or higher speed? I want you to think about this for 5 seconds, because if I was there in person, I would have asked you to talk to a person next to you and do a think, pair, share. But since we are all remote, I just want you to think about it for a few seconds. All right, so it turns out that the correct answer to this is that the final speed, when V final becomes equal to R times omega final, does not depend upon the friction on the surface. And so this is a non-intuitive thing, and that is because there are two things that you have to consider. How much is the coefficient of kinetic friction, and how long does it take for the wheel to start rolling? And if there's higher friction, it'll take a short time. If there's smaller friction, it'll take a long time. But the total amount of energy that is dissipated in the form of heat and all will be the same regardless of how much is the friction. And hence, the final speed is independent. One way to see it is to think about the fact that the angular momentum is conserved about the point where the wheel first touches the ground. And hence, it cannot, it cannot produce a torque there. And so, since angular momentum is conserved, the final speed will not depend upon the friction. Now, this is a non-intuitive problem, and you could tell that professors were having difficulty in solving this problem on their feet while they are thinking aloud in an interview situation. But it was very clear that they actually knew how to solve problems. So there is something to be said about thinking like a physicist. They were using problem-solving heuristics that are still great heuristics that we should actually be helping our students learn explicitly. For example, they were talking about, let me think about the limiting cases. What would happen if there's no friction or there's infinite friction? And these are great heuristics, even though in this particular problem, it doesn't necessarily help you. But we should be teaching students to think about limiting cases. They were thinking about analogies with familiar situations. For example, let me think about the wheels of an airplane when it touches the ground, when it lands. How will the friction on the surface determine the final speed with which it starts to roll without slipping? Again, analogies are great things to do. They also were thinking about, some of them went to the board and drew diagrams. They thought about what is given, where they were going. They thought about the principles of physics. They even thought about conservation laws. Should I be using conservation of energy, momentum? Some even thought about angular momentum. But notice that angular momentum is a tricky thing because you have to think about the point about which the wheel first touches the ground. So the point is that all of these heuristics that professors were using really are great heuristics for physics problem solving. And when we interviewed introductory students, we did not see them using those kinds of heuristics, and they were often going in circles. So one of the lessons that we learned from this study is that it is really important for us to teach students effective problem solving strategies, such as thinking about doing a conceptual analysis, thinking about, limiting cases, thinking about drawing analogies, thinking about predicting the features of the solutions that they might later reflect upon and see whether their predictions was correct or not. And if it was not correct, why is it not correct? What was it about my knowledge structure that made it so difficult for me to solve this problem? And why is it that this is the principle that I should be using? They should be thinking about, breaking the problem into sub-problem, or, thinking about the principles of physics before they jump into looking at some formula. And I must say that everyday life does not prepare students for these kinds of things. So unless we incentivize students with grades and other things to use these incentives, they are not going to actually become good problem solvers, and they will not necessarily learn to think like a physicist. Now, there is another lesson that we learned from the same study, and this relates to the same people being given to another problem. This is the ballistic pendulum, in which you have two putties that are actually on a ceiling. One of them is raised to a certain height, it collides with the other one and then goes to a certain height. And the question is, how does the final height depend upon the initial height? Now, notice that this question was actually given to students, more than 2,000 students in multiple choice format also. And after instruction, you can see only 27% of the students said that you have to use both mechanical energy conservation and linear momentum conservation, because when the thing is coming down, you have to use mechanical energy conservation, and the final speed of this thing coming down becomes the initial for the collision, and the inelastic collision takes place, and then the final of that becomes the initial of the thing going up. Now, this is something that professors didn't even read what the question was. As you can imagine, they have given this kind of problem so many times to their students. They even just looked at the problem and they said, oh, I would use conservation of mechanical energy here, momentum here, and then energy here. That's how you'll solve this. So this was a really easy problem for professors, but guess what? For the students, this was not any easier than the other problem. The problem of spinning wheel that the professor said was so hard. In fact, we even found that some of the professors said, oh, this problem is so easy for my students. It's going to be so easy because I have done exactly the same problem. Guess what? Even their students did not end up doing any better than other people's students. So this is, if you really think about the difficulty of this problem, it is a really hard problem because it's a three-part problem. Notice energy conservation, momentum conservation, and energy conservation. It's a three-part problem in which the different parts are related because the final of one becomes an initial of the other. And if we zip through this problem and think that this is trivial for students, just because you have developed a lot of intuition about it, you are not going to be able to help your students develop a solid grasp of physics concepts. And, they are going to be deprived of developing a good knowledge structure. So the point is that the perceived difficulty of a problem not only depends upon its inherent complexity, but also on how much experience and familiarity and intuition we have built about it. So we need to actually think about the difficulty of problems from our students' perspective. We have to put ourselves in our students' shoes and think about how to solve problems from their perspective. And that is how we are thinking about things, whether we do it in introductory physics or quantum mechanics. So let me now move on to talking about quantum mechanics. Now that I have said that intuition and expertise, are kind of related things. So one of the things that we find is that the kinds of difficulties that students have in learning introductory classical mechanics is very similar to the kind of difficulties that students have in learning quantum mechanics. What do I mean by they are analogous? Well, in introductory physics, for example, the naive notions about force and motion really make it difficult for students to learn, right? So people will say a huge trailer truck must exert a larger force on the small car because the small car gets smashed. And of course, they are getting confused between force and acceleration here, because the acceleration of the small car will be more, but the forces are equal in magnitude and opposite in direction. Similarly, they might say, oh, an object that is moving at a constant velocity must have a net force on it, because I need to give it a larger force to get it moving. Well, I mean, this is again a very hard thing for students to actually understand, that no, the net force, is zero on an object that is moving at a constant velocity. So you can see that people's everyday notions, their naive notions are really making it difficult for us to think about how to help students learn introductory physics. And so we as instructors need to think about their initial knowledge as resources. We need to actually know that only when we actually bring that thing into our instruction can we actually help our students build on that and repair their knowledge structure, organize their knowledge structure, and extend their knowledge structure. In quantum mechanics, you might say, okay, so you're talking about things that don't necessarily relate to, everyday force and motion and other things. It's about microscopic world. But the point is that in quantum mechanics, we are talking about things that are very different from the things that students have already learned in classical mechanics. And that makes it very difficult because, again, there is a paradigm shift, just like the way everyday naive notion going to Newton's laws is a paradigm shift. Similarly, going from classical mechanics to quantum mechanics is a paradigm shift. And if it's a paradigm shift, again, people really start struggling, because once they thought they had really understood position and momentum and how these things are deterministic and they evolve in time, how they evolve in time, now you are telling them, no, these things are just not deterministic. They're probabilistic. And only when you do measurement, you only have certain probabilities of measuring different things. And these are just like, operators that act on states in Hilbert space. And of course, as they say, in Hilbert space, no one can hear you scream. So it is really hard for students to learn quantum mechanics. And we need to, again, think very hard about how to help students develop a solid grasp of quantum mechanics. So we wrote an article in Physics Today on, with my colleagues on taxonomy of student difficulties in learning quantum mechanics, and also how research-validated learning tools such as quantum interactive learning tutorials and peer instruction tools can really help students develop a solid grasp of quantum mechanics. So let me actually give you a couple of examples of the kinds of difficulties we find. So expectation value of measuring some observable, such as energy, for example. It is the average of a large number of measurements on identically prepared quantum systems. So if your state, quantum state, is a linear superposition of the ground state wave function and the first excited state wave function, then students were asked, and this is more than 200 students from 9 different universities, by the way. And we asked them to find the probability of measuring different values of energy when the wave function was a linear superposition of ground state and first excited state, and also the expectation value of energy. And notice that both of these things are 2 parts of the same problem. This is A and this is B. Now you can see that the students did relatively well on the first part. And the correct answer is that if this is your wave function, then the probability of measuring energy E1 for the ground state will be 2/7, the absolute square of this. And the probability of measuring energy E2 will be absolute square of this 5/7, and everything else is 0 because there's nothing else. Now, this is pretty good because 2/3 of the students actually provided correct response. But when you look at the second part, you can see that suddenly the percentage correct has really gone down. What is going on? Well, I mean, the reason we gave this as the second part is because we thought that the students would actually use conceptual reasoning to answer this second question. And they would say, I can use this answer and I can say, if expectation value is the average of a large number of measurements on identically prepared quantum systems, so then if the probability of measuring energy E1 is 2/7 and energy E2 is 5/7, then the answer for expectation value should be 2/7 times E1 plus 5/7 times E2. That will be the answer. That is not the way most students did it. Most students did not use conceptual reasoning to do this problem. They used an algorithmic approach. So they had learned that expectation value is integral psi star, the wave function star, times the operator for energy, which is Hamiltonian, times psi. And notice that if you do it this way and you're doing it algorithmically, you know, there are so many ways to go wrong. First of all, some people forgot there is an integral involved. Some people forgot that there is a complex conjugate. Some people did not take into account the orthonormality relation. And so finally, only 39% of the students got it right. So you can see, I am not saying that people should not use, you know, mathematical approach. What I'm saying is that mathematical and conceptual understanding needs to be tied very closely together. There needs to be something in students' knowledge structure in order for students to actually retain anything. And here you can see that students are not really thinking of expectation value conceptually as an average value of a large number of measurements on identically prepared systems. That is a really useful thing, an important thing for them to know what it means, as opposed to just, can I compute it? I'll give you one more example before I say what are the kinds of learning tools we are developing. So how does the wave function evolve in time? You know, that is another thing that is really important. And again, these days with the explosion in quantum information science and technology, where superposition of states is really important, you know, we also have to actually gate the system. You know, you need to evolve your quantum system in time. And so this is the question again that was posed to more than 200 students from 9 different universities. And they were asked, is the probability density for this state does the probability density depend on time or not? And the correct answer is it does. Because if you think about how the ground state wave function evolves, it's going to be e to the power minus I E1t over h bar, here e to the power minus I E2t over h bar. And when you take the absolute square, there will be a cross term that will not cancel out. So this quantum state is not a stationary state. It's not just the ground state, or it's not just the first excited state. It's a superposition of the two. And so the probability density depends upon time. You can see only 43% of the students provided the correct response. And most of the incorrect responses said, well, you know, like the probability density does not depend upon time because it's just this thing times e to the power minus some constant, I Et over h bar. So time always drops out. It's just a common phase factor. Notice that students are getting confused between what happens for a stationary state and what happens for a linear superposition of stationary state. And this is a really important point because these days we are in the era of second quantum revolution when people are actually able to exquisitely control quantum systems and they are able to manipulate them where they can actually manipulate these superpositions. They can even entangle entangle different qubits, different quantum systems, and they can evolve them together. And so students need to have a deep understanding of these concepts. So, I mean, I can keep giving you lots of examples, but let me say that what we find is that the kind of difficulties students from these 9 universities were having was independent of their background, teaching style, of the instructor and the textbook that they had used. And they were very, they were universal, they were common, similar to the kind of difficulties that you find in introductory level, right? And they were often due to inability to distinguish between related concepts. For example, stationary state and linear superposition of stationary state. So the question is, what can we do? And learning theory comes to our help, right? So cognitive theory says, first of all, that we need to build on students' initial knowledge. If we don't really figure out where the students are and actually provide optimal mismatch, we are not going to be able to help them build a solid grasp of quantum mechanics. So basically, we need to actually use the research on student difficulties as a guide and start from there and build on that and then help them repair and extend and organize their knowledge structure. The good thing is cognitive science also says that people's sense making shows patterns. So whether people I'm talking about what is student difficulty with expectation value, or what is student difficulty with time dependence of quantum state, they will be classified only in a few categories, not infinitely many categories. It's not like 7 billion people on this planet will have 7 billion different kinds of difficulties, because if that were the case, then we as instructors and education researchers will have a very hard time helping the students. But the good thing is that even for expectation values, student difficulties can be classified in maybe 3 categories. Same with, time development, maybe 3, 4, 5 categories, but not infinitely many. And that means we can use those things, whatever we are finding as resource, and build on that. And whatever learning tool we are developing should actually be informed by those, and those things should explicitly be taken into account there, right? And of course, we need to keep students actively engaged using evidence-based approaches to teaching and learning, right? And so we are actually doing these things, and we are actually developing these things called quantum interactive learning tutorials, or QUILs. And these things actually are based on the findings of student difficulties. They use them as a guide. They use a guided inquiry-based approach to learning, in which one thing builds on the other thing. So the students are the ones who are doing the thinking, and they are going through it one by one. We provide hints and feedback as needed. And notice that we are actually bridging the gap between quantitative and conceptual aspects of quantum mechanics, because even quantum mechanics has a very well-defined conceptual framework that we should really help our students learn, because if they don't understand the conceptual framework and they're just learning like how to just do some plug and chug, their learning is not going to be meaningful. So the conceptual stuff is really important in order for them to retain those things. We are using those computer-based visualization tools, and they are often adapted from things like open source physics. We have also done Phys that Antje has developed. We are also using Phys, all kinds of computer simulations into these QUILs that we are developing. And notice that the QUILs are keeping students actively engaged. They actually are things that would be best done in small groups where students can work with each other, because 1 + 1 is greater than 2. Students can actually learn a lot by talking to each other. But you can also give them as homework if you like, so long as you give them the pretest, which you can give after your lecture or something first, and then have them do the quilt, and then have them do the post test that will show you how much more they have learned from the quilt. So let me give you one example of the quilt. So for example, I already talked about the time development of superposition state. So let's say that in the pretest of this quilt, you might say, okay, here is a stationary state wave function. Here is a linear superposition of stationary state wave function. Will the probability density in these two cases depend upon time or not depend upon time? Now, let's say that the student said, in both cases, it will not depend upon time, because the time dependent phase factor is just an overall phase that goes away when you square it. Of course, that is not correct for this quantum state, which is a superposition state. Then the first thing after that pretest that students will do in the quilt is that they will actually go to a computer simulation to check their prediction. So, and here I am showing you time-lapse pictures of what they will see. So for example, for this particular superposition state, what they will see, here I'm plotting psi star psi on the vertical axis, and this is the position. And what they will see, and this is at different time. This is at time t = 0, future time, even larger time, and even larger time. And what they will see for this quantum state, which is a superposition of two quantum state, ground state and first excited stationary states, is that, oh, the probability density is changing with time. I don't see it be constant. It looks different as time passes. At this point, you have caused a cognitive conflict. Students are now in a state of disequilibrium. I predicted something else, and this is not what I'm seeing. So this is a very good time for you to actually use the guided inquiry-based approach in the quilt to actually help them think through why is it that the energy operator or the Hamiltonian operator is very special in this case, and why is it that those stationary states, which are eigenstates of that energy operator, play a key role in how this state evolves in time. And that's why those states, if this was just the ground state wave function, or this was just the first excited state, in that case, no, this is not going to change with time. This is going to be the same every time. But here I have a superposition state. There, that is not the case, and it will actually depend upon time. So students actually learn about this in many different cases of different potential energy. What will happen if you change the potential energy, and how these things would actually use the same principle of quantum mechanics. And you need to think about it in the context of whether it's a superposition state or whether it is actually just a stationary state. And they actually then look at flowcharts and try to predict those things in different contexts. And the scaffolding support that they get is slowly reduced so that students develop self-reliance. So I'm just going to show you for lots of different quills here, the pretest scores after students have done it, alone, and what they do after they actually work on the quills with their peers, okay? And you can see that the performance is much better after working with the peers. I also wanted to say is that we are also developing these things called sequences of clicker questions. And basically what I mean by that is we are developing these multiple choice questions that build on each other. And a lot of these are inspired by quilts that you can use in your class as think, pair, share thing. Each student thinks about it himself or herself, then they pair with other students, and then they share their ideas. You can even use these as review questions at the beginning and at the end of the lecture. And if any of you is interested in the quilts or in the peer instruction tools, please let me know. Here, I'm going to show you some results from this thing for infinite square well. And you can see that vertical axis is number of students. Here, their scores. And this thing is the one in which they did not use anything but lecture. And you can see student performance in this red one is not as good as when two classes actually use the peer instruction tools. You can see that in both of them, student performance is significantly better than this one. Of course, here for the quantum measurement topic, if you use just traditional instruction, the student performance is not very good on the post-test. When they use those peer instruction tools, those multiple choice questions that are sequences, it's much better. But if they also use the quilt, it is even better. I wanted to just quickly touch upon one more topic, that is learning from mistakes. The effect of giving explicit incentives to correct mistakes on subsequent problem solving in quantum mechanics. So basically, problem solving is often a missed learning opportunity. So what do I mean by that? As experts, when we actually really struggle to solve a problem, and maybe we even got it wrong, and then finally we got it right, we often think about what was it about this problem that made it so difficult for us? What can we do with our knowledge structure, and how can we repair it? How can we reorganize it so that we don't make the same mistake another time? In other words, reflection on problem solving is a really important thing. And, Edith Yerushalmi and I basically did a research study long time ago in introductory physics, in which we saw that giving students explicit incentives to correct mistakes in their quizzes actually really improve their performance later on in the exam on transfer problem. What I mean by that is, for example, if we gave them, energy conservation and momentum conservation combined in one problem, in quizzes, and then we ask them, okay, correct your mistakes using books and notes. And later, we gave to those students a similar kind of transfer problem that also involved energy conservation and momentum conservation. What we saw is that students who had been asked explicitly to struggle again productively by correcting their mistakes ended up doing significantly better than control group that was not asked to correct mistakes. They were just given the correct answer. Notice everybody is being provided the correct answer. It's just that students are being asked to correct their mistakes and struggle with the same thing again before they do it. So for example, when you return to students their work first time, you mark it and you say, there's something wrong here, but you don't say what it is. And you just say 5/10 or 6/10 or whatever. And then they have to struggle with it again productively using their books and notes. And then you give them the correct answer, as opposed to in the control group where you just give the correct answer. And since we had seen so much benefit in introductory physics with Adit Yerushalmi and our research, what we found I thought, what about in quantum mechanics? Will we actually see similar kind of difference? Or have the students developed this metacognitive skills where they will actually learn from their own mistakes and you do not have to give them explicit grade incentives to correct their mistakes? Yeah, basically the point was that in that introductory physics case, we had given to students 50% of their points back for correcting their mistakes before we gave them the correct answer. So to make a long story short, because I feel like I'm running out of time, basically, we did the same study in quantum mechanics, and we asked students to correct their mistakes, and we wanted to see, will that make a difference in how they would perform on those kinds of problems on later exams? And so I am actually going to just get to my results here. So when I say comparison groups, these are students who were not given incentives to correct their mistakes. These are students who were given incentives to correct mistakes. When I say pre-test, this means the first time around, how did they did on those problems. Post-test means how did they do after they corrected, the second time around. These students did not correct their mistakes. These students corrected their mistake, and this post means after they corrected their mistake. How did they do the second time around? That's what the post means. And low means the students who had not done well the first time around. Medium means those who had done medium, and this is high. And what you can see is that in the comparison group in which we did not give any incentive to correct their mistake, grade incentive to correct their mistake, and we just gave the students the correct answer, the student performance the students who had performed badly for the first time around, they improved a little bit, but here they improved a lot. Here, not much improvement, not much improvement. Here you can see that even the medium group improved. So in other words, giving grade incentives to correct mistakes even helped students in the quantum mechanics course. In other words, even in these kinds of courses, we should be giving students explicit incentives to correct their mistakes because it's helping those students who otherwise would not actually be able to learn. So making students productively struggle with their own mistakes is a really great tool that teachers can use that is actually going to help those ones who are otherwise not doing well. And notice that, we keep saying that we need more people who are, literate in science and engineering, but if we don't actually help the students who are not otherwise doing well with giving these kinds of incentives, they are not going to actually be able to do as well. And notice that this is particularly helping those students who actually need that help. And so that is a really good thing because we are actually bridging the gap between those who are already doing well and not. So I just wanted to, at this point, instead of actually going to the next topic here, which I was going to talk about, I will just take any questions. So I'll stop because I feel like I've run out of time. Thank you so much for your time.
We thank you, Chandralega. There are so many aspects and so good, important suggestions that we are just taking a lot of notes. So first of all, thank you a lot. And I wanted to underline how you are able to show as inquiry-based learning approach using student reasoning discussion is important. And as ideal experiment simulation is relevant because I believe that without experiencing situations, they are unable to understand. But there are some aspects that I want to ask you to let us know your opinion. One is metaphors. How can we use metaphors and in which way are useful in this field. For example, as far as I know, up to now, I use metaphor to individuate the different way of thinking, the not coherent or not scientific way of thinking. And this is the way in which I use metaphors, because there are alternative models in my mind. So I'm very interested in knowing which is your suggestion for about metaphors. Another point that I will ask you is, you say that we have to follow difficulties of students in selecting the approach in quantum mechanics too. But as far as it is important in classical physics, because they are experienced every day, in quantum mechanics, I have two aspects that are difficult for me. One is, for example, superposition principle means something which is completely different of the superposition, for example, of two waves amplitudes. Is absolutely another thing. They have to understand what means and what Hilbert space is the space of the state instead of the state of the laboratory, the state of the system in the laboratory. So there are some concepts that I use as guidelines for my approach, for the approach that I suggest in quantum mechanics. And I attach the topics following the main fundamental questions. Then inside to them, I use inquiry learning, ideal simulation, and so on. But if I have to follow problem-solving approach and only the way in which difficulties are emerging, how can I build the coherent path that is inside to theoretical idea of quantum mechanics? I hope I am clear.
Yeah, thank you. Thank you, Marisa. So in response to your first question about metaphors, I totally agree with you that, metaphors can be very useful, but we have to be careful so that, students don't necessarily overextend it again. So for example, for quantum mechanics, people often use metaphors such as, let's say that they're talking about superposition and things like that. People say, okay, let's use a metaphor where you have gotten admission into three colleges, like this college, that college, that college. And, over time, you're saying, oh, my probability of going to this college is this, my probability of going to this college is this, and this college is this. As you talk to more people, maybe those probabilities are changing, right, with time. So maybe you are now thinking more about going to Oxford than going to Cambridge or something like that, And so, your probabilities are changing. But once you make your final decision and you say, no, I am going to University College London, then your wave function has collapsed. You are like, okay, my wave function is collapsed. Those other things are no longer a possibility for me. So this is just like doing a quantum measurement. Once you have done the measurement, forget it. It's an irreversible process. Everything else is gone. So you can see that this is a metaphor that you can use to talk about, linear superposition of different things. You haven't made up your mind. You are in a superposition of going to this school, this school, this school. And maybe those probability of going to those is evolving in time. So that's like a time evolution. But then once you have made up your mind, this is like quantum measurement. But again, as I said, metaphors can be good, but students need to realize that there is only so much that these metaphors can give you, right? They shouldn't take these things literally. Now, the second thing that you were saying is that, whenever you talk about superposition and you're trying to talk about quantum state superposition as opposed to, some kind of a classical wave or something like that, one has to, again, be careful in those contexts too, right? Because the thing is, literal translations would actually get us into trouble. And again, students need to realize that the quantum state is an abstract thing. When you talk about wave function, this wave function and superposition, wave function is in a superposition, or the wave function of two particles are entangled in this EPR paradox or something. These things are all like, when we, as soon as we start talking about wave function, we are talking about some really abstract thing.
Yes,
and
we know.
The thing is, as you said, the experiments that you are doing, the quantum experiments that you are doing are happening in your lab. So the point is, in one case, you're talking about a very physical thing. I'm doing measurements in my lab, and I'm talking about what will be the probability of measuring this? What will be the probability, those kinds of things. But then making, since I have prepared my quantum wave function to be something, and it's evolving and I'm evolving it in a certain way, all I can tell is the probabilities of these things. And so I cannot actually directly, connect that abstract wave function, which is not a physical thing. It's just a mathematical way of thinking about what might happen in my lab, in my measurement. So you are absolutely correct. One needs to be very careful about that as well.
Thank you so much.
Well, thank you so much.
Thank you to you. There are some questions, or can you collect questions? I suggest that there are some urgent clarification people can ask now. Otherwise, I suggest to collect in our forum space the questions for Chandralekha, and I will convince Chandralekha to take part to our forum according with her time. So
sure, that sounds good.
Thank you. So some urgent question. We are a little bit late, in fact, as usual, but now we have group work discussions and can be held with time free for working group activities. So maybe no urgent questions.
Okay, so you're saying, Marisa, that we can actually deal with these questions, like during the forum?
Yes, we have a forum, which is for quantum mechanics teaching learning community, GIREP community. We will collect in this forum, and the address of the forum and everything will be communicated during the closing session, because there is a new website in GIREP. We will say it tomorrow, and I will ask you.
So, one person is saying that they wanted to know more about the second quantum revolution in the US. Should I say something about that, Marisa?
Yes, absolutely. Thank you so much.
Yeah, so we had this working group recently about this. And basically we came up with the core concepts that students, even in high school, should learn about quantum information science and technology, right? The idea of quantum computer, the idea of quantum teleportation, the idea of quantum sensing, and how, what is the meaning of, how is a bit different from a qubit, right? I mean, like bit, we know that bit can be 0 or 1. Computers basically process information, and a bit can be a 0, can either be a 0 or a 1. Basically, oftentimes, for example, you might make a bit in a computer, those computer chips, they are made with, they're basically capacitors, right? And if the voltage is above a certain value, it'll be 1. If it's below a certain cutoff, then it'll be 0. What is the difference between bit and qubit? If bit process, bits are used to process information, qubits, are basically things that are used to process quantum information. The difference is a bit doesn't just have to be 0 or 1. It can be in a superposition of 0 and 1. So I think that we feel that these kinds of ideas, so this working group that the Office of Science and Technology Policy and National Science Foundation, as Marisa said, had set up, that I was a part of, basically came up with a set of core concepts that we should really be teaching even high school students, and even earlier, actually, because some of these ideas in a conceptual way, if you start talking about these early, people will understand the value of the second quantum revolution and the fact that we now have exquisite control of these quantum systems, and we actually can manipulate them and evolve them in very, very controlled manner, right? So thinking about what is a quantum computer, what are the kinds of problems a quantum computer can do, what is the implication, why is it that quantum computer can actually do these kinds of things. You know, just some conceptual framework for those kinds of things is really important. And so quantum measurement, what is the role of measurement, right? What is quantum key distribution? And the great thing is that quantum key distribution, now, for example, in Switzerland, there is this company called Quantique that is selling quantum key distribution devices. By the way, I just wrote a paper recently on quantum key distribution, QUILT, Quantum Interactive Learning Tutorials. So if you're interested, I can send it to you. But the point is that these are ideas that we can actually help students learn. And from early on, we can get them excited about it, because otherwise they won't know how exciting and fun the second quantum revolution is and how quickly, you know, this field is actually growing. You know, like whether you look at Europe, whether you look at US, or whether you look at China and Japan and other countries, I mean, this field has exploded. Everybody's talking about quantum computing. Everybody's talking about quantum teleportation, basically, or quantum key distribution and things like that, and quantum sensing. And so getting students to think about these and the fact that there's so much workforce need in this area is really a good thing. So thank you for that question.
Thank you a lot. We know that this is important challenge both in Europe and in US. So we have to follow and we have to go in depth to help people to learn and to prepare new technicians, because we need some different preparation for technician in the future. Thank you. Chandralekha, you are our source, our great honor and the privilege to have your suggestions and your comments is very, very important here and later in our community. Thank you a lot.
Well, thank you so much for having me, Marisa. Thank you.
Okay.
So, Anthony?
I think now we can proceed to the work group meetings, if I'm correct, Marisa.
Yeah.
Just a quick reminder to everyone, the same links that you have used yesterday are available as well today. So use the same links to proceed to the work group meetings, and they are already open. So they're similar to yesterday. One other thing is that we will meet again here in the plenary session, not today. Okay, so when you end the work group meeting today, that is the end of today's session. But we will meet again tomorrow at 3:15. Okay, so I remind you, after today's session with the work group meeting, you will meet again at the work group session at 2. So at 2 tomorrow, you do not meet here, you meet at the parallel session with those links. Okay, and then we meet all together at 3:15. Okay, so basically I will see you because I see you mostly here, or rather you see me. You will see me at 3:15. Okay, so I think now we can proceed. If there are no other comments from the panel, we can proceed to the work group meetings.
May I ask Marisa exactly where we're going to meet Chandra again?
Chandralekha will...
Yeah, please, can you tell me where I need to go?
Back to working group 3, if she can. Now.
Okay. Be in work group 3. Okay, because there was a question in the chat so that she can answer it, and I have some questions as well. Okay.
Can you send my last letter to her with the points, questions we have to discuss, because maybe it's important for her.
Okay.
The questions I send to
participants. There was a question on the chat from Moja Cepic.
And what is the link? What is the link for that working group 3?
Yes, we sent that in the links, but maybe Anthony can do it again.
I'll send you the link in a minute.
Yeah, if you can put it in the chat, I will.
For work group 3, yeah.
Fantastic.
Thank you so much. Thanks a lot.
They already posted it.
We will summarize the questions put in the discussion during the starting session now by Sergey. So
okay,
now there.
Okay, thank you.
Okay, thanks a lot. So I'll go to that other link then. Thank you.
Thank you, everyone. See you tomorrow.
See you. Okay.